In this lesson, we're going to continue our look at the reactions of aldehydes and ketones, focusing on the Wittig olefination reaction. The Wittig reaction, or Wittig olefination, is the reaction of an aldehyde or a ketone with a phosphorus ylide to form an alkene. The term olefin is simply an older word for alkene, so olefination is making an alkene. In the example, we see propanal reacting with a 1-carbon phosphorus ylide to form 1-butene. An ylide is a compound with opposite charges on adjacent atoms which have a filled octet. If we look at the phosphorus ylide shown here, we can see that the carbon and the phosphorus have opposite charges, and each atom has a filled octet. As you might expect, phosphorus ylides are strong carbon nucleophiles. The reaction places whatever group is attached to the phosphorus onto the carbonyl carbon, replacing the carbonyl oxygen to form an alkene. The phosphorus ylides used in the Wittig olefination are prepared from alkyl halides. The reaction involves treatment of the alkyl halide with triphenylphosphine followed by a strong base. In the first example, we see 1-bromo-2-methylpropane treated with triphenylphosphine followed by N-butylithium. In some cases, weaker bases can be used. In the second example, we see 1-bromo-2-propanone treated with triphenylphosphine followed by sodium methoxide. In these examples, we can see that the ylides are drawn differently than what we saw up above. Phosphorus ylides are more typically drawn without the charges and with a double bond placed between the carbon and the phosphorus. The double bonded version of the structure is a simpler alternate Lewis structure of the same compound. The mechanism of the Wittig olefination can be broken down into the formation of the phosphorus ylide and the reaction of the ylide with the carbonyl. The mechanism for the formation of the ylide is quite simple. The first step is a simple SN2 reaction. The triphenylphosphine acts as a nucleophile, attacking the alkyl halide and displacing the halogen as a leaving group. This results in the formation of a phosphonium salt, which is then deprotonated by a strong base to give the ylide. The base that's used is typically tuned to match the acidity of the hydrogen being removed. More acidic hydrogens, such as those adjacent to an electron withdrawing group, can be removed with modest bases such as alkoxides and hydroxide. Less acidic hydrogens are removed with stronger bases such as sodium hydride, sodium amide, and N-butylithium. Once prepared, the ylide can then be reacted with an aldehyde or a ketone. In this part of the mechanism, the ylide acts as a nucleophile. The electron-rich carbon of the ylide attacks the electron-deficient carbonyl carbon. As the carbon-oxygen pi bond breaks, the electrons flow towards the nearby phosphorus, forming an oxygen-phosphorus bond. This results in the formation of a 4-atom oxyphosphatane ring. A cyclic flow of electrons then opens the strained 4-membered ring. The carbon-oxygen and carbon-phosphorus bonds break, and the electrons move to form the phosphorus-oxygen and carbon-carbon pi bonds respectively. As you can see in the last step, triphenylphosphine oxide is formed as a byproduct. The Wittig olefination results in the formation of a new alkene. In all but the most trivial cases, the stereochemistry of the new double bond should be considered. It turns out that the geometry of the product alkene is greatly influenced by the stability of the ylide. In the first example, we see propanal reacting with a stabilized ylide, an ylide with an electron withdrawing group adjacent to the carbanion. In this case, the carbonyl conjugated to the ylide stabilizes the negative charge through resonance. The reaction proceeds to give the product as a mixture of E and Z stereoisomers. Typically, the reaction of an aldehyde with a stabilized ylide greatly favors the formation of the E isomer. In the second example, we see propanal reacting with an unstabilized ylide, an ylide that lacks an electron withdrawing group adjacent to the carbanion. Again, the reaction proceeds to give the product as a mixture of stereoisomers. Wittig reactions using unstabilized ylides typically greatly favor the Z stereoisomer. The reasoning behind why product stereochemistry is so greatly influenced by the stability of the ylide is complex and beyond the scope of this lesson.